but yeah, the next section is on path-native Wasm. This is discussing some of the trade-offs and things we can get out of Wasm and things we can't get out of Wasm. Or sorry, not things we can't get out of, but like just a lot of trade-offs. We just talked about why we might want Wasm in terms of like potentially better performance, better integration with the system where like we already have like, how to put this, like, it's not just the fact that it's Wasm, it's that it works with IPLD natively and all of our stuff is built around IPLD. This doesn't necessarily require Wasm. I personally think we could fix this by having better Solidity code, like better Solidity libraries, but it's still painful. But most of this talk will actually be focused on like the how and less the why. We've already covered some of the why. So let me just describe the problem. So like in an ideal world, we would just take the FVM as it exists today and just say, yeah, anyone can deploy a contract on this or a Wasm contract on this and everything works. Unfortunately, this is not so simple. The first problem we run into is that optimizing compilers don't have nice predictable runtimes. And our compiler that we use to compile Wasm to native, because this is the way Wasm works. Literally, you take the WebAssembly and it compiles it down to your native architecture, and then it runs a bunch of optimizations to make it fast, which means it's really fast. But that process of like compiling and then like running optimizations can be n squared in certain features of Wasm modules. It could be linear in others. It could just have a large overhead in some. And it's very hard to like predict the time this compiler will take. But it just produces nice code. But the other problem is like they're potential compiler bombs where like maybe you put some inputs in and it makes a very large program, or they have some inputs where like it looks like they should be fast, but like they somehow produce a very slow program, that kind of stuff. So this is where things get tricky. The next problem we run into is the lower you get to the hardware, the more the hardware details matter. Where like we like to abstract our machines and think, oh, it's a CPU, it just runs instructions and it just like linearly walks through it. It's not how computers work at all. Computers are really, really complicated. So for example, like CPUs are optimized for nice, well-written programs that optimize well. They're not written for programs that, for example, have like chained memory dependencies or chained unpredictable jumps. Because, of course, why would you write that program? It's going to run slowly. Unfortunately, the lower you get to the hardware and the more, effectively, the more you optimize the user-deployed code, or really, the closer to the hardware you let the user deploy their code, the closer to like your native instruction set, the easier it is for them to take advantage of, or sorry, to like abuse the CPU and like make it misbehave in ways where like just make it slow basically. And how to put this? The tricky part here really is then gas modeling this correctly. Where like right now our gas model is kind of an average where it says, hey, assuming you have a mostly well-behaved program, because we know that most of our built-in actors are well-behaved, like one instruction will take this much time on average. And then we just use that average and it's fine. The problem is once you start allowing users to deploy their own smart contracts to the network, so their own WebAssembly level smart contracts, now they can like introduce a program that just like, again, like it's all it's doing is just like reading some addresses or like reading some bits of memory, but then it's really, really, really slow. But then someone else deploys another program and it's reading bits of memory and it's really fast and no one knows why. So like not no one knows why, but like the network can't tell the difference and it just like, yeah, so that's the problem. There are solutions to this, but the solution is basically to make the gas model super pessimistic, which would then make our existing built-in actors, at least without having two gas models, it would make our existing built-in actors really expensive to run, which wouldn't work. So this is a gnarly problem. We're going to have to talk about potential solutions here, but this is one of the reasons why we can't just let users deploy whatever they want in the network right now. The final problem is the large attack surface. Wasm time has had multiple CVEs. I think it's like 5 or 6. They could have caused huge problems for the network because it's complicated. It's like it's an optimizing compiler. It's not just Wasm. It's actually, I think maybe 1 or 2 of these were in Wasm time. Most of them are in CraneLift, the optimizing compiler. Some of these were sorry, the joke is some of them are even real because like a lot of CVEs are kind of bogus. But most of these were related to like complex features like SIMD and like experimental stuff. But still, like we do want to avoid exposing ourselves to these security problems. And whenever you introduce like complex pieces like optimizing compiler and like letting users basically run native code, you have problems. The final problem is like just CPU and hardware attacks. Where like once you start letting people deploy code that is very close to like the native code that gets run on the hardware, you start having to worry about like actually like people trying to like mess with the hardware itself. Luckily, timing attacks and side channel attacks are less of an issue here because we do run on a specific block time. It should be harder to use those kinds of attacks, like leak information, because there's like you just don't get that time side channel as a property of the network. However, there might be attacks like row hammer and stuff like that, where row hammer is an attack where you keep on sort of hammering on one address, and if you keep on doing that over and over again, you can get bits to flip. So that's something we do have to worry about. Now, maybe this is not an issue because, like, well, the reasons why this might not be an issue are, for example, like it's mitigated in CPUs and in kernels and whatever, where they basically like they pause you if you do it too much. There's also the fact like you have a limited runtime, so you might not be able to run long enough to execute this kind of attack. But still, the closer to the hardware you get, the more you have to worry about this kind of stuff. So we have a couple solutions. The first one is just don't. Like basically say, okay, instead of letting users deploy Wasm the compiler to native, just run it in an interpreter. And actually, the current thing we're thinking about is literally take the Wasm interpreter, compile it to WebAssembly, run it inside a WebAssembly VM, and then interpret the user-deployed Wasm inside the WebAssembly interpreter inside like the VM, which is ridiculous, but this is literally what Substrate does. And this gives us some benefits. One, by running it inside Wasm, we can reuse the gas accounting that we currently have to basically run the gas accounting on the interpreter itself. Two, because it's running inside WebAssembly or inside a WebAssembly container, we get the security of that WebAssembly container. So if there's a bug in the interpreter, we're a lot better off. We can probably also make the interpreter faster by basically removing a bunch of checks because, oh well, if it crashes, it crashes. We have to be careful with that. We have to make sure that it crashes and it doesn't just corrupt memory, but still. Yeah, but like it does give us some nice benefits. It removes the compile step entirely, so we don't have to worry about compile times. There may be some compilation, some intermediate representation, just to make interpreting faster, but that at least can be done on-chain inside a WebAssembly smart contract, so we can easily time it using our current gas model. It mitigates all of the close to the hardware issues, mostly by slowing everything down. Or like it becomes much harder to like attack like memory latencies and stuff like that because everything is just slower. So like each time you try to read something from memory, you're gonna do a bunch of other stuff anyways. That's gonna drown out the cost of reading that thing from memory. This is what we found when we implemented the EVM, where like we wrote some attacks and found that like it doesn't matter. Like with the EVM is so much slower anyways that like it just doesn't matter. You also reduce a lot of the attack surface by avoiding just-in-time compiling. So again, like you can't just like sort of try to like pick a sequence of Wasm instructions that generate a very specific sequence of CPU instructions. And again, you run inside Wasm. The bad part of this is it's very slow. It's not super slow. So like it might be faster than the EVM. We have to benchmark it. Is that?
Yeah, question. How much slower?
We don't know. I have not benchmarked this. So like that is a good question.
And a related question, how much slower to compile to native, but not with an optimizing compiler, just with a non-optimizing compiler?
These are things we do have to benchmark, and unfortunately, I did not have a benchmark before I came here. I probably should have, but that may require some implementation work. But like my understanding is it's kind of orders of magnitude in each case. For like what was the last number I saw? I think was either 2 or 10x for the linear compiler, for the non-optimized compiler versus the optimized compiler. But I have to double check that. You could look up probably, it's like, okay, that's the next thing here. That's a single pass compiler.
Just quickly, I can tell you that pessimistic gas model would be around 2 orders of magnitude, at least for memory, right?
Which one?
Pessimistic gas model.
Yeah.
2 orders of magnitude.
Do you mean 4 or 100?
Sorry?
By 2 orders of magnitude, do you mean 4 times or 100 times?
100 times.
100 is probably too slow, but the reason I ask is because there are 2 big things that feed into the gas cost of something. Mm-hmm. One is the algorithmic complexity of the naive algorithm that we try to execute, and then second is the execution speed of the thing.
Yep.
And we're staring right at a 2x improvement in the built-in actors onboarding model through an algorithmic improvement.
Yep.
We could totally take a 2x degradation in execution speed if that was what unlocks us being able to do native vectors.
So that's the other thing I want to talk about, because like we don't actually necessarily need to make that trade-off, because at the end of the day, we could just have 2 models, and that honestly I think is where we're going to go, or we're probably because like, or maybe even 3 models. It depends what we do here. But I expect that like we will probably have a system where we'll have a set of effectively blessed actors where the network agrees, hey, these actors behave themselves. We're going to make them cheaper for the good of the network. And the second actor becomes common and frequently used. The network can agree that these are well behaved, and in some upgrade, they can just like reduce the gas cost. It's kind of like the way precompilers work in EVM, except you don't even need to implement it like in your EVM. It's just there. That's my thinking here at least. There may also be other like consensus-driven ways, but those become really hard to reason about in terms of like security and economics and stuff like that. Okay, the next thing I want to talk about though is the single pass. Do you have any comment? Okay. The single pass compiler option, and this is kind of a step up from the interpreter option, where here instead of running optimized compiler, instead of interpreting at runtime, you take your EVM bytecode and you compile it in 1 or 2 passes, basically ON passes, or sorry, constant number of passes. You compile it down to native. This is not nearly as fast as an optimizing compiler because it doesn't try to then get rid of instructions. It basically just takes every EVM instruction, sorry, not every Wasm instruction and maps it directly to a sort of a sequence of your native instructions. Effectively, this I think this mostly just helps your CPU pipeline and also reduces some jumping overhead and stuff like that. It partially solves the problem of compiling, although it's still like the step still depends on your native hardware. So we would have to like run this step. We would probably have to run this step outside of Wasm. There may be a way to run part of the step inside Wasm to produce some intermediate representation, then run the rest of it outside Wasm to actually produce your native code. That might help us get better like determinism here, but we'll have to see. Like better predictable compile times. But there's still some complexity there, but it's much, much less complex than like figuring out how to do optimizing, doing an optimizing compiler here. It does not solve the closer to the hardware problem, at least not very well, because like, yes, you can't try to get the compiler to output a single instruction repeatedly or something like that, but you can get the compiler now to basically like output very specific sequences of instructions, like padded together, effectively gadgets. And this could, or probably would still cause some, like, force you to use basically a more accurate gas model to account for pessimistic memory access and stuff like that. So that's the problem with this. Really, yes, we could go with this, but it might actually not be any or much faster than the interpreter, just because we'll have to use a pessimistic gas model to effectively slow everything down, just in case someone has like these like random memory access and stuff like that. Computers assume that you have a CPU cache. So, and we can't really assume the CPU cache here, which makes it hard.
Why not?
Because like, if, for example, I have access to maybe like, basically, effectively, if my actor has access to more memory than can fit in my CPU cache, or I could somehow like figure out like how to like force the CPU cache to like keep on swapping out cache lines, then I can force the CPU to constantly have to go to main memory for every single memory request, and that's one of the biggest problems we run into with allowing people to deploy things natively. Where like with interpreters or with the EVM, it's much less of an issue because there's so much other stuff you have to do. If you say like read this memory address, that like you're basically giving the CPU all of that time to actually go read the memory address. Effectively, like the CPU can sort of look at your section of instructions. It doesn't matter where you put the read; it'll just move the read to the top, speculatively read, run all the other instructions, and then like yeah. So it's a lot better.
Yeah, essentially, actors would be just allowed, let's say, from having more memory than like 2 to 4 megabytes, which is a lot. But on the other side,
it's not a lot. Yeah,
it's not a lot.
Yeah. Now we could also have a model where like the more memory you have, the slower we run things. There are potential ways of like maybe like modeling cache lines and stuff like that, but that gets like very hardware specific and difficult to reason about. But it is possible. Like one thing we definitely can do is we can say, hey, like if you do a contiguous read, so if you do a bulk memory read, we can charge you the sort of like some latency for the first byte and then just bandwidth for the rest of the bytes. But the problem is like unfortunately, because the way Wasm works, you actually have 2 stacks. You have your stack in Wasm, and then you have your stack in like your language, and then the reads in the stack in your language are random. Like not random, but like they're one-off, like small little reads, not like big bulk reads. So like that to Wasm is going to look like a read of memory. So yeah.
Kind of a 2-part question. What's the expected distribution of like popularity of actors? In this case, like, are you going to be calling the same code like, is it a power law where you're going to call one thing like a whole bunch of times, and then there's a long tail that only ever got called once?
I expect that, yes.
Yes.
Yeah.
And I'm also
Personally.
assuming that being a replicated state machine, like it's going to run on more than one machine, right? Like the actual execution will run on several machines.
Probably.
Yes. So why not start with the interpreter? And then if it gets past, oh, we've called this thing 100 times, we'll now try the single pass on it. And if the output is the same as the interpreted run that runs next to it, it's probably good. And we do that a bunch of times.
So we can. The problem is like, yes, like I would like some kind of solution that involves like slowly upgrading things and making them faster and faster. There are sort of sleeper problems there where an attacker could sort of just sit around and like basically put in a bug, let it sleep for a while, and then wake up the bug and kill the network, especially in ways where like, it might be hard to detect that. Maybe like if promoting actors is very infrequent, it might be possible to do this. But on the other hand, if promoting actors is very infrequent, we could also just do it with human consensus, and it's probably not a huge issue. So that's the trade-off there. But.
Yeah, I don't think there is a way to use the double execution, right? Because if I'm an adversary, I'll run, let's say there's misbehaving code in the case of the single pass compiler. I'll just not trigger that function until I get fully upgraded to single pass.
So there is an option here, which might actually make sense from an economic standpoint, where basically, like you say, once a certain amount of Filecoin has been burned on a contract in terms of gas, you can say that that's effectively a down payment, and now you whitelist that one contract.
For attacks like like non-deterministic execution or something like that, that amount would have to be enormous.
But you would need a way of then later detecting actually I shouldn't like this contract is a problem and reverting it.
Yeah.
But the point here is this helps avoid the sleeper problem. It helps avoid the problem of like I start to deploy a bunch of spam and then wake everything up later, because yes, I could still have a sleeper, but like somehow you have to burn like a lot of Filecoin to actually make that sleeper work. Which might be an economic reason here, and like maybe we might be able to pick some numbers here that actually make sense, where like very like commonly used actors will very quickly hit this limit, and maybe people could like pay in to like hit this limit. Like there may be options like that, but yeah. So these are the two things we're currently considering. The plan I'm currently have in my head is like start with interpreter, because this unlocks just deploying WebAssembly, like it blocks deploying WebAssembly right now. It allows people to directly access the IPLD APIs and the more native interfaces, but it does not give you great performance. Like I expect performance will probably be slightly better than the EVM, because like it's going to be 64-bit or 32-bit address space and that kind of stuff instead of whatever. But yeah.
I never saw numbers. What's the difference in perf between EVM and FEVM and FVM right now? Any estimates?
In terms of, it's hard to estimate because we don't have a lot of benchmarks, unless someone else does.
So not for FVM in particular, but when they tried to do the Wasm project and basically just port code directly over and compile down to Wasm, it was on the order of 100 times slower to do it in Wasm than on the EVM. So it's really use case dependent. When that team tracked down the root cause of that, it was because they were doing like really specific, lots of very specific crypto code that benefited from the 256-bit, right? So.
I see. Yeah, we try to delegate a lot of that crypto code into like outside, but yeah. Okay. But yeah, so yeah, this is what we're currently thinking. I guess the first question I have really is like, is this worth it? Because like this does like, it's not going to be like an instant we get better performance. It's not going to be like that. But it would give us again access to native APIs, other languages, that kind of stuff. What do people think? Well, also like I'd actually like to hear like what numbers make it worth it. We can take notes and then like do benchmarking and see like do we match those benchmarks?
So the old saying is make it work, make it right, make it fast, right? This unlocks new things that for programming. Great. I like even starting with the interpreter, even if it's slow, amazing. You can change that decision later.
I agree. The question is like, do we have, the problem is really priorities. We're like, at what point is it worth it to do it? And that's why I'm looking for like how good does the performance need to actually be to be worth it?
Is it a performance question or is it a functionality question?
Both, I guess.
It's a step on the right path.
Okay.
Like it's I don't think, I don't know. I'll posit that there's not a lot of debate about whether like it's the right path. You know, I assert that, you know, getting towards native actors is the right path. It's a step. I don't think it matters if it's slower than comparable EVM code.
Yep.
That's the thing we can fix later.
Yep.
But it unlocks capabilities.
Yep.
And, you know, the programming model.
Yeah. I also like the other way to think about it. Sorry, the other way to think about it as a step is that like it forces us to figure out the code deployment pipeline and really like nail down a lot of other APIs. And it's something we've been using to do just that. So like even if we don't end up like, even if it's not directly useful, it still like really helps bring the FVM towards where it needs to go.
Yeah, it will push you to figure out the block store accessibility.
But yeah. Do we have anyone who's worked with Near here or anything like Near? No? Okay, I was hoping. Because like they use a single pass compiler and I was hoping for their thoughts on this. Okay.
Stephen, quick question.
Yes.
For the previous thing, is part of also the flag that like, not the previous one before that, the interpreter model, like this is doable in not the network upgrade that's happening in November, but like the next one after that. This is like
Possibly,
relatively doable and easy versus other things which would take much more developer time and bandwidth. And so to Brooke's point of like, make it possible and then make it good, like, is this about the most possible, fastest thing that we could do that would be viable and useful and a good step forward?
Yes, yeah, and that's why this was sort of listed as the first step. The question really is like, is the path even worthwhile given the difficulty? And it sounds like people do think it is, but this is a small audience. But yeah, I just wanted to get feedback on this and ideas and potential other roadblocks. Like also, like if you can't think of it now, please come to me later or send me an email or Slack or whatever. Actually, don't do email, just Slack. Because I won't read you, I'm sorry. Or actually file an issue in the FVM if you have any concerns about like things that might be possible or not possible, any ideas on how we could do this. You can also open up a FIP discussion. That's probably the best way of doing this. But yeah, okay. The final thing I want to talk about is we have some questions on interpreters because we have a couple of options here where basically like, or really two paths. Currently, in the EVM, we basically, like the code CID of an EVM actor is the EVM. If we were to do the same thing with WebAssembly, we would say that the code CID of a WebAssembly actor is actually literally the WebAssembly interpreter. The nice thing is we get very clean layering because we wouldn't even touch the FVM at this point. We just layer it directly. It does also sort of help distinguish between native and interpreted, and this is good and bad. So it's not nice or, yeah, it's good and bad. The hard part is it'll be harder to eventually upgrade to native. So like the nice thing about not doing this, like the alternative below is make the code CID the CID of like the code that would be interpreted, and then somehow some other table that tells you if it should be interpreted or executed natively. Then I think that doing it that way is that it means that like as we upgrade code CIDs and say, hey, this code CID should be executed like natively, or like natively, where natively means like on the native architecture or compiled to native architecture. Like it just makes that upgrade path easier. Yeah, the tricky part is it does mean that like the Wasm, like this would be more built into the FVM itself. I'm just wondering if people have opinions on this, like if there's like a hard like definitely don't do it this way or anything.
I have an opinion that native-like is better,
Okay.
And the reason is the same motivation of it's a step down the right path.
Mm-hmm.
It's not the destination itself. The point of the step is to make the next steps easier.
Okay. Then that is honestly it for this session, which means I think
Can
I made
I
up
ask
some
a
time.
quick question
and
on the, sorry, I keep
Oh,
grabbing
sorry.
a mic and then being slow to ask the previous question. Just on the previous slide, when it comes to having the metadata of to compile / interpret or use directly, what is the migration or the next step? Like, is that metadata going to be useful in the future, like, along future
Prob-
paths? Or is this going to be like annoying overhead that we're going to have to get rid of and compile away at some point, or what?
The metadata would be in some data structure we could get rid of it on migration if we needed to, but also I don't think it would be like, honestly, like one of my concerns is I think we will keep the interpreter indefinitely, or at least a single pass compiler indefinitely, simply because like running optimizing compiler is expensive, regardless of even if we can account for gas correctly, it's still expensive. So there will be people who want to deploy a smart contract on chain and then pay the immediate cost rather than pay the cost of running the smart contract, like basically indefinitely, rather than paying the upfront cost of optimizing that. Basically, if you don't expect your smart contract to be called very often, that's exactly what you'd want to do. This might be, for example, useful in like counterfactual interactions and stuff like that, where like you want to deploy a smart contract, but you actually don't expect it to be called, but it's still, well, take that back. And counterfactuals don't need to deploy a smart contract in the first place. But like I can actually no. You don't need to deploy the exact smart contract, but is the code still? Okay, I actually have to think about that more. But like I can still like there still might be use cases where like again it's a very simple smart contract where like all of the other overhead involved in the smart contract is more than like actually executing it, and you just don't care about the cost of compiling it. Or so you care more about the cost of compiling it than it is. Sorry.
I was just going to lodge a vote for the native-like one.
Okay.
Because this is actually very close to some prototypes that we've been doing with libp2p plus Wasm.
Okay.
For some really crazy stuff we're doing in DHT land. And so, yeah, reading these, we decided to go with what the native-like one is like.
Okay, so you have like both interpreted and native, or
Sorry, what was that?
so like are you doing both interpreted and compiled?
Yeah, well, the CID is like the bytecode. I have demos where I'm actually writing in Wasm text format, like the actual code, and the CID points to
Well,
that.
so, yeah,
But
that is
we
what
also then compile to
Yeah.
we can put bytecode too, so you can write stuff in Rust.
Yeah, so I guess like we already are doing that for all of the code, and like regardless, even if it's FVM like, we'll still be referencing the bytecode by CID. We'll always do that.
Yeah.
The question here is like, do I put that CID directly in the actor state tree and like treat that at the same level as the other native actors, or do I treat that as kind of like a next level up where like you put that CID inside the actor's state tree, like the actors like because they have two state trees and it's really confusing. But yeah.
It almost feels like the code should be an array because like for example we talked, okay, we will have Wasm interpreter which will then run Python interpreter that someone might want to run Python light code in.
Yeah, but in that case the way we usually do that is then like the actor itself will have a link to the Python code.
Yeah, 100%. Like for native, I'm saying for FVM, it seems like for that in that model, right? Like the code should be almost like an array because another reason being, I don't know how mutability of the code works exactly in FVM, but it feels like essentially. If we have some guarantees, right? Like for example, let's say we have a guarantee. We say this actor will never change its code. If we have some upgrade methods, if the code exact execution code is in the state,
Yeah, you're
the
right.
guarantees are much weaker.
Then you can guarantee. Yeah, you're right. That's a very, very good point. Thank you. Did you get that one? You still?
So I guess it's also a question of like, well, it's not like a question. It's the question of what do you want the semantics to be, right?
Yeah.
Very different use case, right? But similar to some others, IPVM's doing the native-like thing because it gives us the option to do kind of whatever we feel like. And there's a incentive for the runner to go with the safest, fastest option, whatever that thing is. So if there's a compiled version of it available on the network, they can still run the interpreted version. There's nothing that's going to stop them from doing that. They can. They probably don't want to.
They might not be able to. So the problem is gas counting, where like we probably charge a lot more for the interpreted version because it's going to be running inside interpreter. So
Yeah,
it's
but they can change their gas schedule and be like, yeah, I need to match these semantics over here. Cool, right?
But my point is like for consensus, like everyone needs to either interpret or execute natively, otherwise it won't like. Does that make sense?
they have different gas schedules, or?
So it's like the way, at least the way we're thinking about doing the interpreter is literally we run a Wasm interpreter inside the Wasm VM, and the gas accounting is at the VM level on the outside, so that we account for the cost of the interpreter as well.
I would suggest not doing that.
So we can, that just means we have to basically have like two completely different gas models. And it also means like maybe you could, like, it does make it a little more risky, and it actually makes it a lot harder to deploy this because now we need to actually have a good gas model for like this interpreter. Whereas without that, we just reuse our existing gas model.
Right, so, but what's wrong with that, right? Like, you're gonna make it more efficient for the network, and you're not going to incentivize people to use the.
Yeah, so like this is the third option actually, I guess I didn't include, which is, because really we have two options, run an interpreter inside Wasm or just run an interpreter natively, and then basically have a gas model for that. That is an option. And it would be faster. There are some more security concerns that might take an extra upgrade. I think honestly, like the right answer there is first run it inside Wasm, and then maybe if it's a problem, consider later running it natively and having a new gas model. That's the faster like path.